Hi, my name is Luke Majette, and today we'll be going over the fundamentals between different types of motion capture, as well as comparing the pros and cons of each type. On the most basic level, human motion analysis is the study of the body structure and the science behind observing the body as it moves and performs various tasks. Be it running, dancing, skating, or any other activity, observing the body in motion can produce valuable data about human abilities and human weaknesses, and can be used for other purposes like entertainment. When watching a body undergo motion, it is usually tracked from one or more angles, and oftentimes a model is made of that motion to describe and quantify the motion being observed. One of the subsets of motion analysis is gait analysis, where a patient walks and the quality of that walk is determined via analysis. This is based on the gait cycle, which is made up of steps and strides. A step starts with the initial contact of one foot when a heel hits the ground and ends with the initial contact of the other foot. So from when the left heel hits the ground to when the right heel hits the ground, or vice versa. Strides, on the other hand, start with the initial contact of one foot and ends with the initial contact of that same foot. So think a left foot and then a right foot, and then when the left foot hits again. And when measuring a patient through gait analysis, be sure to consider the individual factors such as the terrain. Obviously, a patient walking on rocky substance is going to be different than walking on flat land, and make sure to account for their gender and age and their height and weight when considering how they walk. Also, be sure to measure different parameters such as their step and stride length, as well as the speed that the patient can walk at and their foot and hip angle. Now, the first type of motion capture that we'll talk about today is called optical motion capture. To gather data about human motion by this method, a large system is needed with a lot of pieces, but the system can produce very detailed and valuable data. Infrared cameras track the distance between the camera and markers on the patient, which are placed at key points of bodily motion, like the joint shown on the skeleton. And on that skeleton, when clusters of markers can be placed together, as denoted by these little red diamonds, you can see these individual segments of the body can be studied individually, and then you can also measure how the segments move relative to each other. So how one leg moves and how that one leg moves relative to the other leg, for example. And back to these IR cameras, at least more than one camera is used, usually two on two separate walls in a room, with 2 points of XY data for the same one marker on the body. A 3D coordinate can be made to determine where that marker is in space. With a lot of these markers, the image of a person is moving is formed by the data, which can then be processed by computer software for analysis, either for animation in entertainment or diagnosis in clinical or athletic settings. For clinical settings, a treadmill can also be used to get a long recording of a patient walking at a continuous rate, which can be kept and recorded for later use or varied to test different speeds, and it keeps the patient in place if you're working in a small environment. Some of these research labs treadmills also have force platforms in them, which are shown by this video to the left. Now, these force platforms, they can determine the amount of weight and pressure being put on a certain part to determine how the body is balancing itself. And these treadmills can get a lot of data, steady data in a small location. And while this is nice, because treadmills are set at a certain speed, the patient loses control over how quickly they want to walk. To further reinforce this idea of two XY planes making a 3D space, here are some examples of a body being tracked through joint markers as it performs different actions. My favorite one is the jump, where you can see each of the little joints as they would have made the jumping motion with the body. Now, the next type of motion capture that we'll talk about is inertial measurement units, or IMUs, which are made up of microelectrical mechanical sensors, or MEMS. These often consist of a 3-degree freedom accelerometer, a gyroscope, and a magnetometer. These come in small form factors and can often be attached to various parts of the body, like the markers from optical motion capture, and they have become very popular because they are compact, affordable, and widely available in the market. The first sensor, the accelerometer, is an electromechanical device that can sense static or dynamic forces, such as gravity, vibrations, and movement. Similar to the idea of a mass hanging by a spring, the amount that spring moves can be measured and analyzed as the mass undergoes a force. The next sensor is the gyroscope, which measures the angular rate by means of the Coriolis force. Like the idea of a mass within the sensor is undergoing a velocity, and when a rotation is applied to the mass, the Coriolis force is experienced, and this force can be quantified and measured to determine rotation. The last sensor, the magnetometer, can measure the Earth's magnetic field, which is used to determine the orientation of the IMU relative to the north and south poles. When a magnetic field affects a current, the charges will be attracted to one side of a metallic sheet, like pictured in the images on the right, which can be measured similar to the idea of a compass. Now, the last type of motion capture we'll talk about is computer vision motion capture, which is much more reliant on computers and benefits from not having any attachable parts to the patient, usually relying on an array of sensors like an IR blaster to track a motion. Both of these Microsoft products are used for different types of motion capture, the Azure for health and technological development, and the Kinect for real-time motion-tracked gameplay. Now, with each of these types of motion capture systems, and as well as the quality of the data that you want to get, there are different price points. For consumers, like low-end stuff like you and me, we'd be buying something along the lines of those Microsoft Kinects, which can run plus or minus $300. For low-scale market uses, like low-budget movies or not high-quality data analysis for personal use, an IMU suit would cost between $500 and $10,000, and camera-based, more optical systems would cost between $2,000 and $15,000. And on the other hand, for research, non-market uses where you are trying to get as detailed data as possible, they can run between $50,000 and $100,000. And in summary, to compare and contrast the three big types of motion capture, optical motion capture, while it is more expensive and physically restrictive, the data that you get is much more accurate and increased visibility. The idea is that you have to have an entire dedicated room just to motion capture with all the cameras in the setup. IMUs, on the other hand, are much more affordable and they're much more portable, but the data is slightly less accurate for extended periods of times, and you don't get absolute positioning relative to the environment. These IMUs are just a suit, so they can be taken anywhere, which kind of opens the door, especially for entertainment. Now, computer vision comes at a low cost and is easy to set up. There's no calibration and there's no attachable parts to the patient. But the trade-off here is lower accuracy, and they're environmentally restrictive and light sensitive. Like this GIF here, this is kind of within perfect conditions, and you can still kind of see the thumb glitching in and out, which is kind of a shame. Well, that's the end of our presentation. We'd like to thank you for watching, and my colleagues' emails are here if you have any questions for a later date, but we'll take any questions right now. Thank you.